Greetings. My name is John Gabriel, and this is the New Calculus channel. Today, I'm going to talk with you about the derivative and differentials and exactly what they are, and I'm going to explain to you precisely what is a differential equation. It's so simple that you won't believe you've never seen it this way before. But the reason for that is that no one has ever actually understood calculus as well as I have. Not Leibniz, not Newton, not Cauchy, not anyone who came before me, not even the great Archimedes. Okay? And I'm explaining these things to you because there's no other way you can understand unless I tell you. I was the first to prove the mean value theorem constructively. I was the first to understand exactly what is a derivative. And it's not that silly little limit of f of x plus h crap that you see in your mainstream calculus. That's just a kludge, which was created to make you think it was made rigorous. But before my new calculus, there was no rigorous formulation of calculus. So, without further ado, let me begin to explain to you all these details. So, I didn't mean to start like that. I meant to start like that. So, now, what is a derivative? Really, a derivative is just a function, okay? It's just a function. That's all it is. And how is a derivative formed? Well, imagine for one moment that this point here that I'm pointing to with my hand lies on a particular function, okay? We don't really care right now what that function is. And imagine that this here is a tangent line to the function at that point. The derivative is just the slope of this tangent line length. So the derivative is formed from the x-coordinate of that point and the slope of that tangent line. Do you understand that? Let's see how it works. So this here is the length, 0.37, as you see here is the length of this line. It's also the slope of this line. So if I move this, see, that blue curve that you see at the bottom, that's the derivative, okay? So that particular line there that I'm coloring in with all these different gradients is the derivative. So, what is a differential? Well, a differential is what comes on the top of the vinculum. Okay, do you see this green line here? It's called a vinculum. Same with this black line. Anything that comes in this particular format, if you see dy dx, dy and dx are called differentials. And they're very well defined in the new calculus, but in your bogus calculus, they don't exist until you supposedly take the limit. Also, in your bogus calculus, you're told that you cannot really separate the two, but you do it anyway when you try to find the indefinite integral. That's because you've been taught by morons the last 400 or 500 years, and you're now hearing the truth for the first time. In order to find out more about how these are defined in my new calculus, you'll have to study it. And I'm going to just focus briefly now on what is a differential equation. So the antecedents or the numerators and the consequence or the denominators here are called differentials, okay? So dy is a differential, d squared y is the second order differential. Dx squared doesn't mean dx times dx, it means the second order differential dx. And you can separate these in the new calculus, and you can do many incredible things that you won't imagine not in the next 50 years because you're simply not as smart as I am. And no one else, excuse me, no one else who has lived before me has discovered those facts. But I'm giving you subtle clues right now. And some of you who decide to study the new calculus and read over those lessons that I posted on my website, etc., Who knows, perhaps you might be able to get close to where I am right now. But at any rate, that's what a derivative is. It's really just a function which consists of the slopes, okay? The slopes of another particular function. Okay, that's how it's made up. And the second derivative, obviously, would be the slopes of the tangent lines to this particular function, right? So this differential equation that you see actually has a solution. This is the solution. Okay, let's just take that out. You see that? So this was the derivative of the blue function, all right? So this is the blue function here. See that? Yeah? And this is the second derivative, this green function here, which is, in fact, the length that is equal to the slope to this red function here, okay, which is y dash x. And in fact, the solution is really f of x is equal to log x, which is also known, this differential equation is also known as the Euler-Cauchy differential equation. Really, there's nothing incredible or remarkable about it. And you can form your own differential equations by starting off with some function and then just differentiating it and then making sure that both the sides are equal. Like, for example, you see here, if we take the first derivative of log x, it's 1 over x. And if we divide it by x, we're going to get the second derivative, which is minus 1 over x squared. Does that all make sense to you now? So remember, what I want you to take away from this lesson is exactly what is a derivative. This is all that it means to be a derivative. It's got nothing to do with limit crap that you learn. It's got nothing to do with all the bogus nonsense that you see in textbooks that have been printed the last couple of 100 years or so. Right? This is a derivative. And you'll learn a lot more once you study my new calculus, because the new calculus is the first and only rigorous formulation of calculus in history. Differential equations are actually dead easy. Partial differential equations are also dead easy. But of course, when you see this and you go through your entire life wondering, thinking that these are rates, they're not rates. Nothing here is changing, by the way. The slope of this particular log function has been the same throughout history and continues to be the same, okay? Nothing's changing. And we don't even speak about a rate here because it's not a rate unless it has a time differential, all right? And even then, in this particular case, it's not a true rate because it's modeled by this function, which, of course, doesn't change. It's never changed. It hasn't changed in past perpetuity, and it's not going to change in the future. So unless you're a moron like that Professor Gilbert Strang from MIT or any of the other morons who agree with him, chances are you are a moron yourself, but not all of you are morons. So I'm going to just let you think about that on your own. This is all a derivative is. It's not there's no such thing as an instantaneous rate of change. That's just a load of garbage. In fact, an instantaneous rate of change is impossible because in your definition, your finite difference quotient, you can't have h is equal to 0, and yet you need h equal to 0 to find your derivative. Don't write in my comment section that I haven't studied real analysis, you fucking idiot. I know real analysis better than anybody on the planet. And if you're a lecturer, open your ears and your eyes and learn from me. I am the great John Gabriel, the discoverer of the first and only rigorous formulation of calculus in human history. More advanced alien civilizations may already know of it. Well, I hope you've enjoyed this presentation and that you will join me again next time for another interesting lesson on calculus or an exposition of some fallacy in mainstream mathematics, actually mathematics, because they've never done mathematics. So till next time, this is a new calculus channel, and I'm John Gabriel. Goodbye.